Hello everyone, this is Harshita and welcome to Group 9 presentation. So today in this presentation we will be talking about the SDVEC, which stands for Software Defined Vehicular Edge Computing with ultra low latency. So let's get started. So first we'll give you a brief introduction of the topic, and then we'll see what software defined vehicular computing infrastructure is, and followed by ultra low latency connected vehicular networking. Then we'll see what big vehicular data enabled system orchestration is, and finally we'll provide a brief conclusion of what we discussed. So coming to the introduction, autonomous driving has attracted a considerable community interest, which drives the demand of intelligent vehicular systems and connected transportation to ensure that ultra-low end-to-end latency is provided. So such connected and autonomous vehicle applications rely on fast mobile networking that keeps end-to-end communication latency down to 1 millisecond range as compared to the 20 to 100 millisecond range in the conventional communication protocol based vehicular computing networks. So the reason why we see this 20 to 100 millisecond latency is, first, the data transmission rely on initial control signaling storms, which employ closed loop physical layer protocols like three-way handshake with thousands of control messages for power control or channel estimation in a single physical link. Second, routing and scheduling in networking take a significant amount of time in computation and information gathering. Thirdly, the high mobility of CAVs incurs tremendous overhead and complexity of protocols, which in turn causes considerable latency for reliable communications. Lastly, the cloud-based models require vehicular data to be transmitted to and stored in data centers, thus increasing the chances of information leakage or loss and longer than expected latency, which could even result in fatal accidents. Next, we talk about edge computing and software-defined paradigms. So edge computing is a new computing paradigm which provides an alternative to eliminate the reliance on remote data centers for mobile applications. By moving the computing resources to the proximity of data sources, edge computing basically enables large amount of real-time and low latency big data processing. So this paradigm removes the network bandwidth constraint to send all the data back and forth to the cloud. Next, we'll discuss about the SDVEC. So this employs edge computation to enable ultra-low latency vehicular services, particularly for connected transportation. SDVEC seamlessly integrates the intelligence, which is the computation capability, into anchor nodes which connect roadside access points via backbone networks. So to fill the gap for ultra-low latency mobile applications, SDVEC replaces the protocol-based vehicular networking with computing-based architectures that support edge computing. Next, we talk about the software-defined vehicular computing infrastructure. So data plane, control plane, anchor nodes, access points, and the core network with a cloud computing. These are the components of software-defined vehicular computing infrastructure. So first we'll discuss data plane and followed by control plane in detail. So first, the wireless grant-free data plane. So it basically serves as the foundation of SDVEC infrastructure, through which an ultra-fast vehicular data plane with high reliability is developed. So it exploits latency minimum open loop transmissions and extends multi-user detection techniques to support contention-free wireless access. It also provides multi-path based error control mechanisms to ensure reliability and supports the potential of dynamic radio resource assignments. Secondly, we'll talk about the scalable software-defined control plane. So this describes the essential network management tools of SDVEC that provide the capability of real-time control of vehicle operations with evolvability and adaptiveness. Particularly, an effective scalable control plane is designed to ensure unified network status and control coordination among distributed anchor nodes. So this control plane provides the following functionalities like optimal placement of the multiple controllers and also the distributed controller consensus. So next part will be discussed by my teammate Sandesh.
Thank you, Harshita, and hello everyone. My name is Sandesh and I will be talking about ultra low latency connected vehicular networking. Emerging and growing vehicular applications requires highly differentiated networking and computing capabilities to be integrated and deployed over the same vehicular infrastructure. To support infrastructure as a service for applications and latency minimum association between vehicles and infrastructure, we develop a virtual cluster orchestration and vehicular network virtualization. In each virtual cluster, a vehicular application is provided with the ability to control, optimize, and customize the underlying resources without interfering other services' performance, leading to cost-efficient operations and enhanced quality of service. Authors have described the design of dynamic clustering and edge network slicing in the following. First is latency optimal vehicle centric clustering. As we can see in the figure, by forming vehicle centric virtual clusters within SDVEC, each vehicle is served by a selected subset of neighboring access points via open loop transmissions and coordinated multi-point techniques. Such a distributed transmit point architecture via front haul link between an anchor node and a cluster of access points can significantly boost the coordination gain of access points, eliminate cluster edges from the severe inter-cluster interference, and in turn reduces vehicular network latency. Second is eco-vehicular edge network slicing. It uses distributed multi-agent reinforcement learning to combat power-hungry edges while assuming system reliability and data rates. This solution outperforms conventional scheme in energy efficiency and system reliability and coverage. The virtual network framework also serves the security of virtual networks. Next is big vehicular data enabled system orchestration. With both instantaneous and historic data, big data driven optimization allow intelligent real-time decision making in a wide range of services. The correlation between vehicular events and data traffic can be extracted to make optimal decisions on resource allocation and caching, anticipatory mobility management, and system security and privacy issues based on long-term strategies. And accordingly, deployment and operational costs are significantly minimized with improved network efficiency. It is categorized into three parts. First is joint data caching and computation offloading. Edge computing at anchor nodes can push the frontier of computing applications, data, and services away from centralized cloud computing infrastructure to the logical edge of the vehicular network, thereby enabling analytic and knowledge generation to occur closer to the data sources. Second is data-driven anticipatory mobility management. Anticipatory mobility management aims at predicting the proactive network association in the future by using machine learning techniques. Specifically, instead of using GPS information of vehicles which consumes huge communication bandwidth and jeopardizes privacy and security, data analytics at anchor nodes can use the past history of access point association vectors to predict the access point association at the next time slot. This data-driven framework simply avoids probing complicated dynamic channel states and losing predictions accuracy due to inaccurate GPS data. And the third is virtualization enabled security and data privacy. Based on virtual clusters and resource slicing, SDVEC can realize vehicle infrastructure as a service to greatly facilitate system security and data privacy. In this paper, authors have proposed a lightweight dynamic cipher that strengthens the security of systematic stream cipher, that is a sequential uplink and downlink data. Sequential uplink and downlink data transmissions between vehicles and edge infrastructure, while retaining the desired ultra-low latency networking. At first, a fingerprint-based dynamic stream cipher as shown in the figure is developed, where vehicle's fingerprint is non-linear time dynamic function and can be shared only between the vehicle and edge anchor nodes. A simple fingerprint vehicle's historical connection to access points, which is unique to each vehicle and aware by the access nodes. Next is, this fingerprint-based cipher can further exploit proactive resource allocation and edge analytics to secure the entire SDVEC with the help of authentication, fingerprint generation and verification, and edge network dynamic and fault tolerance. For data privacy, anchor nodes can filter or pre-process sensitive data information while releasing the computation burden of vehicles. This approach avoids information leakage in black hole and cloud servers and thus make SDVEC less fragile to privacy issue. Authors of this paper are implementing this paper solution for smart and connected infrastructures in real-time CAV deployment. They are currently building an in-lab experimental testbed for SDVEC architectures, and this is fully functional prototype for an SDN-based edge network and computing platform. And the conclusion is, in the next 5 to 10 years, ultra-low latency connected transportation will reshape autonomous driving and human society. Major development efforts in vehicular edge computing and wireless network infrastructures are facilitating the practical deployment of massive CAV technologies. Thank you.